Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 29, 2025, so just 2 days ago. This paper introduces a fascinating new model for taking a complex 3D object and intuitively breaking it apart into its core components. In a user study, its generated decompositions were preferred over 65% of the time against other methods. The paper is titled Bang, Dividing 3D Assets via Generative Exploded Dynamics, and the results are really quite stunning. And to kick things off, just look at this first figure. It shows a beautiful exploded view of a futuristic mechanical humanoid, with all its internal components laid bare. The authors used their framework, Bang, to create this. It works by repeatedly applying a process they call Generative Exploded Dynamics. This is the core idea, where the model learns to smoothly pull an object apart, piece by piece, while keeping track of how everything still fits together. They also enhance the detail of each individual part, resulting in this incredibly coherent disassembly. So how does this process actually work under the hood? Well, this diagram lays out the whole 4-stage pipeline. First, there's exploded data synthesis, where the system learns what a decomposition looks like by studying examples. Next, the core exploded dynamics generator uses that knowledge to produce the exploded view for a new object. After that, a trajectory optimization step refines the movement of each part, ensuring they can be smoothly reassembled. And finally, controllable generation lets a user interactively guide the process, like selecting a specific wing on an airplane to separate it. Drilling down into that generator stage, this diagram shows the core architecture. The authors use a pre-trained then adaptation approach. They start with a powerful pre-trained latent diffusion model. Think of it as a generative AI that's already an expert on 3D shapes, and they keep it frozen. Then, they add 2 new lightweight modules shown in red. The exploded view adapter takes the input object and a timestamp, and the temporal attention module ensures the resulting animation is smooth. This setup efficiently teaches the big model a new skill, creating these continuous, exploded views. Building on that adapter architecture, this diagram shows how they enable user control. The system accepts what it calls spatial prompts, like a 3D bounding box you draw, or a specific surface region you select on the model. These spatial instructions are then encoded into tokens, which are a kind of language the model can understand. These tokens are processed by dedicated prompt transformer blocks, which then communicate with the main adapter. This allows the user's specific request to directly influence and guide how the model decides to break the object apart. Alright, moving to the results. This next figure really puts the approach to the test against other methods. On the left, you see the input objects, a treasure chest, and a robot. The middle column shows results from 2 other segmentation methods, which is the process of dividing a digital object into parts. You can see the results look quite messy, almost like shattered glass, with fragmented pieces. But on the right, the decompositions from this new model are incredibly clean and logical. The parts are volumetric, meaning they're solid, not just hollow surfaces, and look like they could be easily reassembled. So those visual comparisons are convincing, but the authors also provide the numbers to back it up. This table shows an ablation study, where they test their model by removing key components one by one. They use 2 main scores. Weighted IOU checks how accurately the generated parts match the real ones, so higher is better. The SEF objective measures how well the part surfaces align, so lower is better. As you can see, removing either the temporal attention module or their gradient stopping technique hurts performance. The full model gets the best scores, showing both components are crucial. So putting it all together, this work presents a really compelling solution to a tough problem in 3D design. Instead of just creating static objects or messy segmentations, the Bang framework gives us a way to intuitively deconstruct and understand 3D assets through its generative exploded dynamics. The results are clean, controllable, and semantically rich, offering a new perspective on creation that feels much closer to how humans think. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.